Thank you very much. I need to tell you the story about how I got an asteroid named after me.
All right.
I went to Caltech, wanted to be an astronomer. I was in desperate danger of flunking out as a Caltech astronomy major. Switched to geology, got to know some of the people involved at that time, this is the mid-70s, in the search for asteroids that could potentially collide with Earth. This was just getting started. The principals were Gene Shoemaker, who you might know, and Eleanor Helene, who you probably don't know. But they were two teams who used telescopes to take photographs of the sky and find asteroids that had orbits that could potentially collide with the Earth. They were the first. Glow became a good friend. Before I graduated, she came up to me and said, Kelly, how would you like to become my observing assistant and help me in this search? And by that time, I had sort of realized that my career was not in professional science, and I declined. So I went off and joined the staff of Sky and Telescope. And fast forward to 1983, I was getting married to my lovely wife, Cheryl, who would have been here tonight, except she had a previous date with a Chardonnay. And so lo and behold, on the occasion of our marriage, Glow, Eleanor Helene, had an asteroid named after us, Beatty. Now, the thing about asteroids is if you discover one, you get to name it, but you can't name it for yourself. If Bill Waller were to discover a comet, it would be known as Comet Waller automatically. But if you discover an asteroid, he would have to name it after, whoever gives him the most money. So, please. So we have this asteroid named after us, and the number is really low. Asteroids both get names, but before that, they get a number sequentially as their orbits are determined reliably. And right now, the numbers are up in the 150,000s of the numbered asteroids. My asteroid is 2925. I did this a couple of months ago. There are like only 50 people alive who have asteroids with numbers lower than mine who are still alive. So there you go.
Not a good sign, Kelly.
Is yours a potentially hazardous?
It is not. It's this obscure main belt asteroid that I've never even seen through a telescope. So on our wedding day. On our wedding day, yes, I know somebody with a big telescope. On our wedding day, at our wedding, in the middle of the ceremony, the priest announces, "I want you all to know that Kelly and Cheryl have had a star named after them." Now, for those of you in the know, you can't have a star named after you. Only the International Astronomical Union can do that. It was something of a joke back in those days, and that company, the International Star Registry and others still exist, and they still will sell you the name of a star for, I think it's up to $75 now. It's completely specious. So the priest announced that we'd had a star named after us. And at the reception afterwards, everyone was coming up to us and saying, "Oh, Kelly, Cheryl, how lovely that you have a star named after you." And I said, "Well, actually, it's not a star, it's an asteroid." And they went, "Oh, well, I guess that's okay too." All right, so now we're going to talk about asteroids that hit Earth in inconsequential ways. We're going to start with talking about meteors. I don't know how we planned this, Michael, but tonight is the peak of the Geminid meteor shower. And how many of you actually looked up into the beautiful night sky as you walked into this building from your car tonight? A few of you did, hoping maybe to see a stray Geminid fly by. I didn't.
No, it's just being ticked off at the moon.
I see. Yeah, well, you've been talking to Mario too long. Anyway, the study of meteors is an interesting one. We're going to get into it. It means high in the air. And so think about it. Meteorologists are people that study the air. Right? It's not about meteors per se. And they occur all the time, day and night, 24/7, all over all the Earth. And on a clear, dark night with no moonlight, you can see maybe a half a dozen per hour from a really dark location. These are sporadics. These are little grains of ground up asteroid that are just floating in interplanetary space that happen to hit the Earth. And in fact, I cited this number and I remembered it correctly. There are roughly 25 million meteors per day worldwide, and not many of them make it to the ground, but it's a very common everyday thing. Today, I did an interview for WBUR's Here and Now, which goes nationally, and they, for some reason, there is this like science media fascination with meteor showers. It doesn't matter how obscure the meteor shower, they want to know where and when to see it. And I do interviews on this all the time. So we'll get to the Geminids in a minute. And so these meteors deliver hundreds of tons of interplanetary material to our planet. We had an interesting discussion about this over dinner time. Sometimes they land as chunks of stuff, but sometimes they're just microscopic particles. And if you, on any given day, if you were to go to your rain gutter and run a magnet along it, you would probably pick up little bits of iron-rich stuff, tiny particles, some of which might be micrometeorites that have drifted through the atmosphere and landed in your rain gutter or on your roof. So when you see these things in the sky, there is a progression of how we describe them. If it's just a brief flash of light, we will call that a meteor or a shooting star. Sometimes it's called shooting stars. If it's really bright enough to really cause you to catch your breath, then we call that a fireball. Those are roughly up to the brightness of Venus in brightness. If they get brighter than, I'm sorry, anything brighter than Venus is considered a fireball. If you see it flash across the sky and go kapow, it has broken up in the atmosphere as it descends, and that is called a bolide. That is the kind of object that is both larger and large enough to have fragmented in the atmosphere at the tail end of its passage. And when that happens, there's a very good chance that meteorites, pieces of that, will have fallen to the ground. And so we have lingo for that too. When this object, before it hits Earth's atmosphere, is called a meteoroid. Think of it as a very tiny asteroid. Then when it goes traveling through the atmosphere, it's a meteor. And when it hits the ground, it should have hit the ground, it's a meteorite. It's all too confusing. I don't pay attention. So, you know, there have been historical records of shooting stars ever since roughly for 6,000 years. But only in recent times have we realized where they came from. This is no woodcut. There are Chinese and Korean records, and they were thought to be atmospheric phenomena, as were auroras, by the way. There was a great scientific debate about auroras, just as a little aside, between Edmund Halley, Halley's comet fame, and a guy named Jean-Jacques Desmoulins, who Halley thought that auroras were effusions of gas from the Earth, glowing gas. And Desmoulins thought, no, I think it's some kind of phenomenon of the sun. And Halley said, no, the sun's atmosphere couldn't possibly extend so far as to the Earth, but actually it does. Anyway, the same thing happened with meteors. They were considered to be some sort of phenomenon. These are the meteors in the sky. And so there came a time in 1833 with a meteor storm. A storm is when you get more than 1,000 meteors per hour. That's one every few seconds. It gets your attention. And there was one in 1833. This is a woodcut showing what was imagined. And this led independent astronomers to realize, first of all, that they must come from outer space. That it was too intense, it was too widespread. Now, they might come from outer space, but they rarely actually make it all the way to the ground. Most meteors happen at an altitude of 60 or so miles above the ground. And these particles are traveling very, very fast. Very fast, okay? So, Michael, if I were to throw a pea at you and hit you in the forehead, right, it wouldn't be too much of a deal. If I were to fire that pea out of a gun at, say, 30 miles a second, it would leave a nice hole in your head because of all the kinetic energy, right? And so these particles arrive with tremendous amount of kinetic energy, which gets transferred as drag, as friction with the upper atmosphere. And what happens is, if you think about it, yes, the particle itself is burning up, becomes incinerated. But what we see as a meteor is actually, and I'll show you some pictures of this, it's actually the tiny straw pencil of superheated air along the path that gets heated to a couple of thousand degrees, and we see that as this incandescent light. Now, those are sporadic meteors. Those are ones that happen all the time, anytime, day or night. We have a different class of meteors that we call meteor showers, like the Geminid meteor shower taking place tonight, which typically are not caused by asteroids, but rather by comets. Comets are these frozen mud balls that originate from far out in the solar system. And when they come near the sun's heat causes the surfaces to vaporize. And so as the gases escape, they carry a lot of the grit with them. And so along the path of the comet might not be anywhere near the sun, but along its path, which could be short out to the orbit of Jupiter or very long, like Halley's Comet that goes out past the orbit of Neptune, over time, grit, a river of rubble, if you want to think of it that way, is just constantly circling the sun along this comet's path. And if the Earth passes through that path, if the path intersects Earth's orbit, then every year as we go through that point, we get a pulse of meteors in the sky. We call that a meteor shower. And those are caused by debris from comets. Oops, I'm sorry, I got ahead of myself. This is the very famous comet Hale-Bopp. And I'm showing you this because it has two tails. The upper one, the blue one, is gas that has been energized by the sun and become either ionized or at least excited, and it's giving off light. And the rosy colored stuff, that is dust escaping from the nucleus of this particular comet. And it is that dust which gets distributed around the orbit. Okay, so seen up close, this comet dust is very fractal looking. It's a very irregular, very low density stuff. And in fact, for those of you, anybody here older than 50? Therefore, you know of grape nuts, the cereal, grape nut cereal. I have a sample of grape nuts with me. It turns out that if you think about it, those of us who are engaged in public outreach, grape nut cereal is roughly the size, the color, the texture, and the density of what I expect a typical cometary particle to be. So the next time you give a talk about meteors to somebody, just bring a box of grape nuts with you and all will be explained. Now, the thing is, when these grape nuts hit the ground at, say, 133,000 miles an hour, which is roughly 50 miles per second, they pack a wallop, equivalent to a Mini Cooper slamming into you at 40 miles an hour. They get all that kinetic energy, you know, force equals 1/2 mv squared. The v squared becomes very important in that equation. So this is a series of images showing a meteor in the sky. And I want you to notice that there's a bright head and a tail. Technically, that is called a trail, not a, a train, not a tail. And so this stuff is going through the atmosphere very high. It excites air molecules along its path. Some of those air molecules are merely excited, that is to say they get heated, but most of them become ionized. And the streak that you see is actually, as I mentioned, a very thin column of ionized gas, which has been heated to a couple of thousand degrees. And as it cools, it gives off light. And that's the light that we see that is the meteor. Here's a sequence showing that same object. Oops, I gotta let the animation run. There it is. And sometimes for the very brightest meteors, after the fireball has gone by, you can still see this train glowing in the atmosphere, that streak of light. That's a very powerful impact at that point. That might be something, rather than the size of a grape nut, maybe a pea to the size of a cherry. Okay, so it came to pass that in ancient times, every August was seen, at least over Europe, a pulse of meteors, what we would now call a meteor shower, around August 10th. And they were, in folklore, they were called the Tears of St. Lawrence. St. Lawrence was a martyr who was martyred on August 10th in the year 258. And the folklore was that these were the tears that he shed as he was being martyred, showing up in the sky. But why were there so many? And it fell to these two guys independently in the 1830s. Edward Herrick, who was a bookstore clerk, and John Locke, a schoolmaster, both were in Connecticut. No, wait, Herrick was in Cincinnati. Anyway, they independently concluded that these repetitive meteor displays in mid-August must be from a periodic source, and this is what we have come to call the Perseid meteor shower. And we call them the Perseids because they all appear to radiate from the constellation of Perseus. I don't wish this on any of you, but somebody has to tell you, it's going to snow. And when it does, as you're driving in your car, all of the snowflakes appear to be coming straight at you, right? As you're driving along, but you know in your head that they're just falling down. So that's a perspective effect. Your motion is causing all of these snowflakes to appear to be coming from one direction. It's the same thing with a meteor shower. As Earth encounters these particles, they all appear to be coming from one direction in the sky, symbolized by these train tracks. And so in the case of this is what it looks like if you were to take a time lapse, they would all appear to be coming from that spot on the left-hand side of the screen. And so in the case of the Perseids, which happened in August, they all appear to be coming from the constellation of Perseus. That's how these meteor showers get their names. But we don't call them, they don't come from the comet Perseid, right? Or they don't call from the constellation Gemini. In the case of the Perseids, it's from a comet called Swift-Tuttle, and every mid-August we pass through its path around the sun, and we get this peppering of the little particles along its path. Now, the Perseids are the most famous meteor shower. I think pretty much everybody knows about the Perseids. It comes at a great time of year. Perseus is already up in the sky at nightfall, so that means you can start seeing the meteors right away as soon as it gets dark. It's summertime, people are out, right? It's a great family activity. And you can see there, this is a plot from a few years ago. They don't always happen just on that night. They happen some days before and some days afterward, but there is a peak, and that peak is usually pretty pronounced. Sometimes the peak for a meteor shower lasts a few days. Sometimes it only lasts for a few hours. There'll be a meteor shower coming up in early January called the Quadrantids, where the peak lasts for a few hours. And if that peak happens to be at 2 o'clock in the afternoon, Boston time, you don't get to see any of them. But if it's in the middle of the night, you see more. It's also the truth. This is a little bit subtle. Earth, this is looking down on Earth as it spins, okay? The sunrise side is the direction that Earth is moving along its path in space, just like this, okay? And so meteors are coming from all sides, but because the Earth is moving along its orbit at 18 miles a second, a given meteor, a given particle, because if it's hitting on the facing side, it's got the Earth's velocity added to it. So a given particle will make a brighter meteor, gram for gram, than if it's on the trailing side. The trailing side is the evening side, and the side where the little guy is standing is the morning side. So generally speaking, any given meteor shower will be stronger in the hours after midnight than it is in the evening hours. Not always the case, but usually, simply because they're faster. These are the main meteor showers during the course of the year. There are lots of smaller ones. The International Astronomical Union recognizes roughly 100 different meteor showers, but most of them are pathetically weak. These are the strongest ones. And the two big ones that everyone knows about are the Perseids and now the Geminids. The Geminids, December 13th. Gee, when's that going to be? It's tonight. And as it turns out, the peak is timed for about an hour ago, Boston time. We are in the sweet spot. But you know that Friday the 13th is an unlucky day, and we're unlucky because, Mario, what's going on in the sky? A big fat moon, right? Which washes out all but the very strongest meteors. So they appear to come from the constellation Gemini. And I don't know why that cursor is frozen in the screen there, but it is. In any case, and they radiate from that point. Just off about where the cursor is, a little bit farther, is the planet Jupiter, which is very bright right now, and a little bit farther up is that moon, which is going to be with us, unfortunately, for a few days. The Geminids do not come from a comet per se. They come from an object named Phaethon. Now, the Geminids as a meteor shower have been known for quite a long time, but the source was not known until 1983, when this object, Phaethon, was discovered. And it turns out to have an extremely short orbit, only about 3.5 years. And its perihelion, its closest point to the sun, is only about 14 million miles. It's way inside the orbit of Mercury. When Phaethon comes closest to the sun every 3.5 years, its surface heats to 1400 degrees Fahrenheit. And that's hot enough for the rock on its surface to literally break down, crack and sputter, and send bits of rock flying off into space. So it is literally, in a sense, a rock comet. And so that's what these Geminids are. They're going around the sun in this very tight orbit. The purple line is the orbit of Mercury. Earth is the blue line out there. And when we cross it, we cross this river of debris shed by Phaethon, and we get a lot of meteors. The Geminids are actually arguably the strongest meteor shower of the entire year, stronger than the Perseids. From an extremely dark site in a moonless sky on a really good night, if the peak is timed for time, you could see 150 up to 150 Geminids per hour. That's a couple every minute. That's a lot of meteors. I've never seen that many. Few of us have, because we live in a light polluted environment. But if you were able to get outside and get in a really dark location, you would be able to see that. This is the Geminids are also rich in fireballs. And so even with that moon out there, Mario, you have a chance to see some Geminids tonight, and some of them might be fireballs, because there's a distribution of particle sizes, which astronomers calculate. Some meteor showers are very rich in big particles, some are very rich in small particles. The Geminids are one that tend to create a lot of fireballs. So,
2 questions.
yes.
Typically, how big of a rock is a fireball?
Raisin Bran.
Yeah, a raisin and bigger, up to the size of a cherry, maybe. It doesn't take much. It depends on the speed. Now the Geminids are a relatively slow shower. The Perseids hit at, I think, I want to say the maximum is 70 kilometers a second, which is about 40 miles a second. So that's the fastest they can enter. The faster they enter, the brighter they're going to be. But that's roughly the size. And the second question.
The second question is this object, Phaethon, is that?
Phaethon, yeah, Phaethon.
Have we calculated how big a rock is it?
Yes, so the question is, how big is Phaethon? It's not that big, it's only a few miles across. And so it doesn't take much to generate a lot of debris. If you think about the volume calculation for something 3 miles across, you can get a lot of raisins out of that, you're saying that, so to speak. So all the time at Sky Telescope, I would get these reports. I thought I saw a bright meteor last night. I am sure it hit the ground. Well, if all you see is a simple streak of light and then it's gone, there's no chance. If you see something that explodes or fragments in the sky, sometimes you'll see like independent explosions along the path, then there's a very good chance that maybe you'll see something will have reached the ground. If you hear thunder, that's another good indication that something has reached the ground. And if you find a jagged hole, for sure. Now, there are a group of people around the globe who have gotten very good at pinpointing the locations of meteorites that might make it all the way to the ground. It turns out that aircraft radar from like airports, tracking planes coming in are very good at seeing objects on their way to hitting the ground. And whenever there's a big fireball that's seen, these sort of citizen scientists, if you will, they go rushing to the airport radar nearest them, and they can identify with pretty good precision where these objects might have hit the ground. And there are a team of, team is too strong a word. There are wild gangs of people who will go anywhere in the world if they think that there's a fresh meteorite fall, because they're worth a lot of money. As I said, 25 million meters per day. How many of them hit the ground? Well, roughly 50,000 each year. That's a few hundred each day. Leave things that are roughly a half an ounce, 10 grams. And it totals a lot per year. And yet, very few of them are actually seen to hit the ground. That what we make a distinction between a meteorite that is found on the ground, that's a find, versus one that is seen to fall and you go and pick it up, that is a fall. Yes, your question.
What does the impact site look like on this? Has it slowed down?
Yeah, so what I want you to imagine is that you're in an airplane and you drop a bowling ball from the airplane.
Gotcha.
Okay. It will reach a terminal velocity of a few hundred miles per hour.
Okay, gotcha.
Right. And so when I would get these reports, I saw a meteorite hit the ground and it started a fire. Nope, not going to happen. Because remember, these objects are in the cold of space. They get cold soaked. Right? They're very, very cold when they enter our atmosphere. Yes, they get flash heated, but only on their skins. They're not heated long enough to penetrate all the way through. They literally land cold. And so very few of them, only 100 or so each year, are actually seen to fall until they hit the ground. Okay, this is supposed to be the next slide. I'm engaging your internet here. Okay, let's talk about a few of the more famous falls in history. 1492 was the first time that a meteorite was seen, the flash was seen in the sky, followed by something they saw it hit the ground. This is the first fall observed in 1492 in what is now Entachine, France. And so this is the one and only stone that fell. It was a big one, 280 pounds. If you ever happen to go to Entachine, France, they have a whole museum dedicated to this one stone. You can take a picture of it just like this. Then fast forwarding a little bit, in 1807, in the town of Weston, Connecticut, which is in the south central area of Connecticut, there was a report of a meteorite that had fallen to the ground. And so Yale University dispatched a couple of astronomers to go check it out. And they interviewed people and said, yes, there appeared to be this stone that fell from the sky, and here's the stone. Word of this reached Thomas Jefferson, who was a pretty good citizen scientist himself, right? I'll get to this quote in a second. There are only 3 presidents who have ever looked through a telescope at the White House. Jefferson owned a telescope. He was not one of them. He left his telescope back at Monticello. I'm sorry, only 2 presidents, not 3. Only 2. Who can name those 2 presidents? Who thinks they know who those presidents are? Shout it out if you think.
Can you guess who they're not?
No.
Obama.
All right, Obama was one. He actually hosted 2 star parties at the White House during the International Year of Astronomy and thereafter.
John Quincy Adams.
And it was not John Quincy Adams. Jimmy Carter.
That's
And the reason is Jimmy Carter was an engineer by training. Recall, he had adolescent children in the White House while he was president. Chip Carter, his son, had a C8 that he took to the roof of the White House and showed the family some stargazing occasionally. So Jefferson, not an astronomer who looked at through a telescope at the White House, said that I'd rather believe that Yankee professors would lie than stones would fall from the sky. Well, he was wrong. And so fast forward again, here's another famous fall in 1954. So we're celebrating now the 70th anniversary of this famous fall, which fell through a house. You can see the hole in the roof there, upper left, and hit this woman. The poor woman got struck, Ann Hodges, as she was lying on her couch taking a nap. And thank goodness that the roof broke the momentum. She ended up with a pretty bad bruise,
Yeah.
right, on her. So that is a famous one. More recently, in 1992, seen across much of the United States, it was a Friday night. And there were a lot of, this is the fall, there were a lot of high school football games around. And guess what? People used to carry around these things on their shoulders. They recorded video, right? A video camera. There were a lot of these in the stands. And so this thing came screaming up the East Coast. And a young girl, she was only, I think, 17 or 18, was at her home. And she heard this calamitous clunk. And she went outside to find the car that she had just bought from her grandmother for $200, trashed by a meteorite that was found underneath. There's the hole, there's the meteorite. Her car was toast. But please don't feel too bad for Michelle. The meteorite sold for $50,000. The car sold for $25,000. So she made a pretty penny off of that. Recently than that, a decade ago, in 2013, February 15th in Russia, South Central Russia. It's 9 o'clock in the morning, but it's winter time. It's February, so it's still dark. They're very far. Look what's coming across the sky. This is from a dash cam. Everybody in Russia has a dash cam because there's so much corruption. Yeah.
О, нихуя метеорит, блядь.
Внимание,
Ебануться.
So forth.
Нихуя себе.
Famous Chelyabinsk
Охуеть.
impact. Chelyabinsk was one of the most powerful impacts in the last century. It was probably about the size of this building when it entered the atmosphere. It packed 440 kilotons, 440,000 tons of TNT equivalent kinetic energy. And something like this hits the Earth on average about once every 50 years. The strongest one before that was Tunguska in 1908. And so I want you to notice this path. This is a very oblique path through the atmosphere. What happened is, this is 9 o'clock in the morning, most people were at school or at work, and they saw this flash in the sky, and everybody went running over to the windows to see what was going on. Then the shockwave hit, shattered all the windows, and most of the injuries from Chelyabinsk were from broken glass, striking people who were clustered by the windows in order to see it. But it was a very powerful event. It left what's called a Struenfeld, or Struenfeld. Struenfeld is the German version of that, whereby the biggest, it broke apart in the atmosphere. You saw that in the street. The heaviest pieces fall first. I'm sorry. The lightest pieces fall first, and the heaviest pieces are carried farthest down along the path. And so you get this distribution along a street. You can see the scale there, it's 1 mile, with the heaviest pieces at the far end and the lighter pieces at the other end. Now, this is February in Russia, in the depth of a very cold winter. Everything is covered with snow. And so all of these fragments fell from the sky into snowbanks. And so there was no way to actually see them on the ground, but if you were walking along and you saw a snowbank with a hole in it, chances are if you dug down, you would find a little piece of Chelyabinsk meteor. This is a little piece of Chelyabinsk meteor. We can look at this afterward, okay? Now, there were some big pieces for sure. This is what, I didn't include that. Doggone it. All right. The biggest piece was recovered in a lake, and I left that part out of this version. I'm sorry. Even more recently, there was a big observed fireball over Viñales in Cuba about 5.5 years ago.
Oye, pero lo vi yo, porque la luz me volvió loco. Dije, ¿y esta luz quién está soldando?
No, pero de todas maneras tú no estás
It's
viendo.
in the sky. Here comes the-
Escucha. Entra, Sandy.
And pieces of meteorite fell all over the countryside in there. So it's a very dramatic event. Here are some of the pieces from that fall. It was recovered, And, for these poor farmers and stuff, if they gathered enough of these, when the meteorite hunters swooped in, they made a pretty good reward for finding these pieces of rock. The largest known meteorite is actually still in place. It's in Namibia. And it was discovered during some time ago. I mean, all the local people have known about it. It weighs more than 60 tons. It's still in place. It's not been moved. Fell about 80,000 years ago. So these meteorites are not all the same composition when they fall. They have different compositions. Most of them are what we call ordinary chondrites. If you think about how the solar system formed, as the solar nebula, the swirl of disk surrounding our sun, gradually cooled from several thousand degrees down to, everyday warmer, cooler temperatures, things condensed out in a sequence depending on what their melting point was. And so in the very earliest days, the rocks that came out of that solar nebula were very primitive. They were little bits of this and little bits of that, almost together. And so most meteorites that fall to Earth are what we call these ordinary chondrites. They are unprocessed, they're primeval, they're essentially the same way that they formed 4.5 billion years ago. And I'm sorry, let me describe these other ones here. In addition, the carbonaceous chondrites form much farther from the sun. They're much more rich in carbon, also water and occasional organic stuff like even amino acids. Achondrites are meteorites that have been melted to the point that they have formed a crystal structure. All right, so they were molten at some point. And stony irons come from essentially the cores of asteroids. Think of the Earth. Right? Crust, mantle, core. The core is made of iron mostly. And so many asteroids melted, large asteroids melted out in the asteroid belt, and they assumed that same structure with iron in the middle. The iron sank to the middle. If you then pulverize that asteroid and shatter it into pieces of that core would be floating around in space. And when they arrive at Earth, they are essentially entirely iron. This is a piece of what was once a core of an asteroid. It's a piece called Sikhote-Alin. It fell over Russia in 1945, and it fragmented as it was entering the atmosphere. That's why the shape is so ragged. It's basically shrapnel. You have a look at that when we're done too. Okay, so asteroids collide in space. And sometimes this is how the core ends up coming to Earth. And it turns out, just within the last couple of months, astronomers, when an asteroid is shattered, let me back up to this. When two asteroids collide in space, the particles basically keep the same orbit as the precursors had, whichever the more massive one was. So if like I'm a giant boulder flying along in the asteroid belt and something comes and shatters me, I break into a lot of pieces, but by and large, I keep the same orbit, okay? But there's some spread. And over time, you get what are called these asteroid families. These are the fragments of larger collisions that have taken place. And this distance along the bottom is in astronomical units. 1 astronomical unit is the Earth-Sun distance. So these are roughly 2.5 to 3 times farther away from the sun than Earth is, basically on the far side of Mars' orbit between Mars and Jupiter. And the eccentricity of that orbit, that is the elongation of it, is plotted along the vertical axis. So astronomers have recognized that there are all kinds of these asteroid families, and it turns out that only a few of those families, the Flora, Vesta, Carina, and Coronis families, are responsible for most of the asteroids here on the Earth. This is brand new stuff just in the last month or so. It turns out that they were able to analyze the fall rate when an asteroid shatters. Primarily, the particles are meteor size, and then over time they become the what are left are kilometer size, because those are the ones that don't get perturbed and come to Earth. they've taken this information and they've been able to conclude that the vast majority of asteroids on meteorites on the Earth come from these two families. The Massalia family and the Coronis Corinne family represent roughly 75% of all the meteorites that are falling on Earth right now from these two impacts. It's not quite as helter-skelter as we thought. There are some very definite places where these meteorites are coming. Okay, so here's the statistics. Statistically, a 1 kilogram asteroid falls somewhere here in Massachusetts every 5 years. I am not aware of any known meteorites that have fallen in Massachusetts. If you go to the databases, it shows a Lowell meteorite. And I have traced this down, and apparently it's just a typographical error. No one that was found fairly recently, like within the last 100 years, no one in Lowell knows anything about this. I think it's specious. So I know of no meteorites that have fallen in Massachusetts. This is a typical ordinary chondrite. You can see that mixture there. This is what the carbonaceous chondrite looks like, much more dark and carbon rich. This is that formation of the core and the breakup leading to the iron meteorites like this. This is a very common meteorite that is known in Argentina called Campo de Cielo, or Campo for short. There were 30 tons of this stuff that were found. If you wanted to buy a meteorite for the best bang for the buck, get a Campo. You can get it for about $1 a gram, right? So 28 grams per ounce. So for $100, you can get a 4-ounce meteorite, something roughly the size of this, right? To have. That's pretty good, right? And it's commonly available for meteorite dealers. Please do not buy meteorites on eBay. Bad idea. Go to meteorite dealers, they're commonly around. From the core mantle boundary is where the metal stops and the stone begins. And the stone is a high density silicate known as olivine, or peridot is the sort of semi-gem name for it. And I have a sample of a palisade, what's called a palisade here. We can take a look at that afterward. If you look through it, part of it is metal and part of it is sort of transparent, beautiful gem-like colors here. I brought all the tricks tonight.
Yeah.
Okay, so this is an example of a page from a meteorite dealer's website. It turns out, what are those two up on top? Martian meteorites? Lunar meteorites? Is that possible? Yes, it turns out that you can own pieces of the moon and Mars for your edification and delight. This is a piece of the moon. This is a piece of Mars. So we can have a look at those when we're done. Right, so they are not only from asteroids. You can get meteorites from these other planets. There's the asteroid belt for scale. Someone has done statistics, and it turns out that if something strikes Mars down here at the bottom, it has about a 5% chance of being swept up by the Earth, and it takes about somewhere between 1 and 20 million years drifting around through interplanetary space before it reaches us. Technically, meteorites from Mercury and Venus are possible, but they are unlikely. And so Mercury, because it's so close to the sun, you need to have enough kinetic energy to get it out to the Earth, fighting the sun's gravity. Venus has a very thick atmosphere, so it's unlikely that something that, even though Venus is roughly the size of the Earth, if you strike it, the air resistance will be tremendous, and we are unlikely to see any meteorites from Venus. But we know of lots of meteorites from the moon and Mars, hundreds of them, and I've got pieces of them here, right? And theoretically, we can mostly get meteorites from rocky planets, the 4 that we know, along with, these are these are craters on Mercury. These are places that could have been sources of meteorites coming to the Earth from Mercury. Technically, it is possible. Someday, a meteorite might be found that is from the planet Mercury. People are looking for them. We haven't found one yet. Right? I talked about Venus and that dense atmosphere. There are craters on Mercury. Some of them, by the time the objects get near the surface, they tend to break up. It's like, kind of like a shotgun blast. So you get multiple craters. Mars is the place that we know we have meteorites from, and I'm going to preempt the question that I know I'm going to get. How do you know it's from Mars? Bill asks. How do we know it's from Mars? Because we have spacecraft that have landed on Mars. We have analyzed the composition of the Martian rocks, the crust, and in particular, we know the composition of the gases in the Martian atmosphere. When these meteorites land on Earth, they trap little tiny bubbles of atmosphere in them that, when analyzed, match the gas ratios that we find on Mars. And they're igneous rocks too also. So we know this is an example of when something slams into Mars, it only needs to hit the escape velocity, which on Mars is only about 4 miles per second. And we can easily reach that with a high impact explosion from a particle. I'm not going to attempt to explain this in the interest of time, but essentially far away from the actual impact site, the surface gets pushed into space by shock waves, kind of a spalling pattern that happens. And some of these particles, these slabs, can get ejected into space at greater than the speed of escape. As I said, it's 5 kilometers per second, roughly 3 miles per second. Compared to the Earth, Earth is much faster. It takes a much greater escape velocity. Now, where did these impacts on Mars come from? The meteorites from Mars? We're looking for fresh craters. And, Mars is a geologically diverse place like the Earth is. Some rocks on the surface are much older than others. When a meteorite gets to the Earth from Mars, we have 3 ages associated with it. The first age is, what was the age at which this rock crystallized from lava? In the case of the Martian meteorites, many of them are roughly about 300 million years ago of origin. So there has been volcanism on Mars up until the fairly recent geologic past. Those meteorites that are of that age, that's when they would have crystallized on the surface of Mars. The second age that we're concerned with is, how long did it take that rock to get to the Earth? Now, the rock circles around in interplanetary space, eventually finds its way to the Earth. All the time it's doing that, it's being exposed to cosmic rays and intense space radiation, and those leave telltale traces in the crystalline structure of the rock of the meteorite. So we can tell when a meteorite falls to Earth how long it has been just migrating through space until it reaches us. And the third age is, how long has it been on the Earth? Right? If it's been on the Earth for a long time, there's danger of contamination and things like that. That's why ideally you want to find a meteorite as soon as it lands. So we have a place, this crater called Zunil is a very fresh crater on the surface of Mars, and this is suspected as being one of the places where meteorites have been shot off into interplanetary space. And so this is what a chunk of the moon looks like. These are a little out of order. I'm sorry, I apologize for that. We know this is from the moon, similarly, because we have samples of the moon. We know what the moon is composed of. We know that the moon's surface has these chunks of this mix of dark and light colored material. The light chunks come from the highlands of the moon, the heavily cratered part that's usually in the southern half of the hemisphere. And the dark stuff is from the Maria, the dark lava-rich plains. The little cube, by the way, is 1 centimeter on the side, same here. This is a piece of Mars that fell. It was actually seen to fall in 1911, might have killed a dog when it landed, called Nakla, very famous. This is another Martian rock called Zagami. Because of, in this case, there was quite a bit of it that fell to Earth. And so this is more readily available than a lot of other Martian meteorites. Even so, it's pricey. A piece of Nakla, a 7-gram piece, that's 1/4 of an ounce, a few years ago, will run you several $1,000s. So if you want to start collecting Martian rocks, you'll need to have deep pockets. Now I want to close with this notion. It's easier to get a meteorite off the surface of Mars than it is to get it off the surface of the Earth. Earth is difficult, both because it has a higher escape velocity and it has to get through atmosphere to escape, right? So the notion that you can hit Earth, it's possible. We haven't had any recent really big craters, but hundreds of millions of years ago, there are craters on the Earth that are 20, 50, 100 miles across. Those would have been big enough potentially to spall stuff off of the Earth and send it flying off into space. But it's much more likely that pieces of Mars ended up on the Earth in great profusion. You saw that we actually have hundreds of these, right? And in the past, when the impact rate was a lot higher early in the history of our planet and Mars, impacts happen more often. There should have been more meteorites in space. More Martian meteorites should have fallen on the Earth. So a theory has arisen called panspermia. It goes like this. All things being equal, Mars, all of the inner planets, all the terrestrial planets started off very hot and molten and very uninhabitable. But they cooled over time, Earth cooled over time, and eventually became a nicer place to be. But Mars reached that point sooner. Mars is a smaller planet, right? The volume goes as the cube of the radius. Mars would have cooled off a lot faster, sooner than the Earth. Perhaps we know Mars had water. We know Mars had a thick atmosphere. Maybe Mars was a habitable place. Maybe Mars was inhabited. And some primordial asteroid fragment slammed into Mars and sent pieces of rock flying that contained spores of life. Pretty wacky idea. But let's explore that a little bit. These two guys, Fred Hoyle and Chandra Wickramasinghe, not the same Chandra who Chandra spacecraft is named after, came up with this idea of panspermia, and it goes like this. If you expose a bacterium or some sort of microbe in space to radiation, it is very quickly going to get zapped by ultraviolet light and cosmic rays and no longer be viable. But if you encase that microbe in a rock, then you afford it some protection from this radiation, and the thicker the rock, the longer it can last. So if you have a rock that is 1 meter in diameter with microbes at its center, then it could last more than 1 million years in outer space before the radiation finally overcomes the microbe. Now, you heard me talking about million-year timescales for these Martian meteorites to get to the Earth. It would only take a spall of roughly 10 feet across to last 14 million years, which is plenty of time to get from Mars to the Earth. So hypothetically, if you had a Mars rock blasted off of its primordial surface, carrying a bunch of microbes inside, they could have made it to Earth with the microbes intact, right? And so then the question becomes, well, how much radiation would they have endured? This is an example of your high school beaker with a very high dose of gamma rays on it, and yet there are microbes that can endure very high doses of radiation and still thrive. So this notion of staying intact, staying viable on this long trip to the Earth from Mars is not totally crazy. So the question might be then, did life begin on Earth or get transferred to Mars? Or is it the other way around? Did life begin on Mars and get transferred to Earth? Thank you very much for your time. Thank you. I just want to say, for those of you who are listening on Zoom, thank you for coming tonight. Unfortunately, you are not going to get to see the meteorite collection that I've got here in front. You saw what I've got. I have the metal shrapnel from Senior. I have the Mars rock, the Moon rock. I have a piece of Chelyabinsk. This is a very interesting piece right here. This is a slice of a meteorite that was seen to fall in Australia in 1969. It's called Allende. It's one of those carbonaceous chondrites that has a lot of carbon inside, but more importantly, it has little tiny white specks in it, which are the first things ever to condense in the solar nebula. This is the oldest piece of solid stuff you will ever touch, Well, you don't get to touch it because it's got the plastic, but this is the primordial of primordial meteorite. All right. One last thing I'm going to show you is this is a slice of an iron meteorite, and it's sometimes meteorites instead of being sold whole, they get sliced up, especially the metal ones. This one shows an interesting texture in it, which is a crystallization texture called Wenmundstetten. And it's telling you that this cooled very slowly to create this crystal pattern, very characteristic of certain iron meteorites. Okay. And these are great guys, but you see. Are there any questions? Yes, Michael.
Over here,
Yes, Michael.
comments. You said that 75% of meteorites come from asteroids.
No. 75% of meteorites come from asteroids in these two particular families.
Right.
All asteroids, I know where you're going with this. Every meteorite that we have has come from an asteroid. We know of no meteorites that have come from comets.
Okay, that's what I wanted to dig into a
Right.
little bit. Why?
Why? Because they're this is your word for the day. Friable. Can you say that with me? Friable. Yes. That means it's crumbly.
Yeah.
Right. And the structure of comet, we know it's a very fractally loose thing, styrofoam, right? And so it can't make it to the surface. Now there is cometary material on the surface of the Earth. NASA has high altitude planes that fly in the stratosphere, and they have these big paddles that scoop up material. They do capture grains from comets, but there are no intact pieces that land on the ground that we can say are cometary. There have been suspicions, right? When somebody calls me and says, "Oh, some big thing landed on Kelly, some big thing landed on my lawn." Well, describe it. Well, it's really icy. All right, describe it. Well, it's blue. Well, okay, that came from the toilet of an airplane.
Yeah.
Catch my next. Other questions here, and then we'll go to Zoom. Go ahead.
Drives the value of these meteorites? Is it people collecting, or is it scientific research, or?
Right. So his question is, what drives the value? It's two things. How little of it was found, right? If I've got 30 tons of iron meteorite found in Argentina, iron meteorites are pretty common, and there's a lot of it. So the cost will be relatively low. If I've got a piece that fell from the moon, right? This is the piece from Mars. It's a piece of Mars. Wouldn't you pay more for a piece of Mars than a piece of an asteroid? And so this is necessarily going to be higher. Often these are much smaller, although there are a lot of individual Martian meteorites. Each one is actually quite, except for Zagami, very small. So it's a matter of what you desire having in your meteorite collection. That, you know, it's a buyer's demand.
So it is sort of stamp collecting.
It is like stamp collecting, yes.
I was wondering whether it was driven by, research institutes that.
Yeah. So what will happen is, let's say you find a meteorite, and maybe I said this at the beginning, or maybe I just said it to somebody. Suppose you find a meteorite and you want to know how valuable it is or what it is. Typically what will happen, say there's only one stone. Your grandfather was using it as a doorstop or whatever that might be. You say, "Oh, I think this is a meteorite." So you send it to one of the places that studies meteorites. And typically what will happen is that they will keep a piece of it for their collection in exchange for telling you what it is and giving it a pedigree. So now you can go to the market and say, "This is certified to be a Shergattite," which is a known meteorite from Mars. Right? Meteorites take the name, they're all named, they take the name of the locality where they're found. So Allende, for example, that little slice, the very ancient one, fell near the little town of Allende in Mexico, right? And so forth. So that's what drives the value, and also, it's what people really are itching to have. I took a group of people down to, in my retired life, I coordinate tours for Sky and Telescope, often involving eclipses. And about a year ago, I took a group of 20 people down to the Yucatan to witness an annular eclipse of the sun. One of the people on that trip was a young couple. He was a cardiologist from New York City, making big bucks, and he was a meteorite collector. And we swapped all kinds of stories about meteorites. And at the end, I don't get tips when I go on these tours. He said, "Kelly, come on, can I do something? You've been so great. Can I do something for you? Do you want a meteorite? What do you want?" And I said, no. He says, "No, what do you want? You want a lunar? You want a Martian?" And I said, "Okay, I'll take a lunar." And so a couple of days later, his dealer provided me with, a slice of the moon. So who's going to turn down an offer like that? Yes.
Are there meteors that we don't even know of that they'll just be on the ground, but
Yes.
they're not?
Yeah. Her question is, are there meteorites that have fallen to the ground? We didn't see them fall. Are they there or not? Yeah, absolutely. An ordinary chondrite, for example, typically a meteorite, when it falls, regardless of what its composition is, will gain a flash fused exterior called a fusion crust, which is quite dark, but it's only just a thin layer. And inside the whatever the meteorite was is still intact. But often they don't have that fusion crust, and it will look like an ordinary rock. And you would kick it and not, because it's got roughly the same density as Earth rocks. Now, if you ended up kicking a piece of iron meteorite that has a density of 7, you will stub your toe and you'll know that something is odd and you'll reach down and pick it up. But you literally could kick a meteorite not knowing it was a meteorite because it looks just like an ordinary rock. And that is the case. Often a meteorite will be known to fall, and it doesn't fall in a nice sandy Sahara, where you can just go over there and pick it up. It might land in the frozen tundra of Canada or in a jungle, right? Or in someplace uninhabitable like Naples, Florida. Oh, sorry, Mario. So yes, they exist. They exist on the ground. And so, for example, a diehard meteorite hunter, especially in the Southwest, they'll do a weekend trip where a common characteristic of all meteorites is they have some iron in them. Some iron. They may not be an iron meteorite, but they have some iron in them. And so these guys that got nothing better to do, they'll go out in the deserts of Arizona and they'll just use their metal detector all day long, looking for things that go beep, 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 and often they come up with a meteorite.
On the screen, they're chomping at the bit. Can we go over there and then we'll come back and finish up
Yes.
the room?
Who had the question on Zoom?
Vivek had his hand up.
All right, Vivek, go ahead.
Yeah, could you please repeat the name of that website that is an authentic meteorite trading spot or whatever?
Oh, I actually didn't give a website per se. But what I would suggest you do, Vivek, is just do a Google search on meteorite dealers. And so they have names like meteoritemarket.com, mrmeteorite.com, stonesfromheaven.com. And what you want to do is you want to take a look and see, if you're interested, get a sense of whether it's a legitimate dealer, ask for references. What you don't want to do is go on eBay and buy a meteorite from somebody who is Shiesty Dealer 8765. That's really asking for trouble. But there are plenty of legitimate meteorite dealers. In fact, every year in Tucson, Arizona, many of the meteorite dealers of the world converge on Tucson. They take over all the hotels and they buy and trade each other's meteorites. And it's quite a feeding frenzy during that time. So there's no one website, but I think if you do a Google search and use a little bit of a filter to judge which ones have legitimate looking websites and are like giving you a lot of information about the pieces that they have. For example, when I bought some of these, they will tell you the weight down to a fraction, a thousandth of a gram sometimes. And that's a hint that maybe this is somebody who's legitimate.
Okay, thank you.
Anybody else? Yes, Alan, go for it.
Hi, thanks. Great entertainment, very informative. Thank you so much. I have two questions. Number one, how do you find and identify a piece of Mars as a meteorite on the ground?
Okay, I touched on this a little bit. We have had spacecraft on Mars, and those spacecraft have analyzed the composition of rocks on Mars, and also the composition of the atmosphere. Now, the thing about Mars is, like the Earth, it is largely a planet covered with igneous rocks. These are rocks that were once molten and they have solidified. So if you find a meteorite on the Earth that is, first of all, an igneous rock, then it is probably not from the asteroid belt. It must be from either the moon or Mars. These are, or the asteroid Vesta. There are relatively few asteroids that were ever volcanic. So that's a clue. If it's fairly either very, very ancient or very young, I can imagine an asteroid that could have been molten 4 billion years ago, but I can't imagine one that was molten 300 million years ago, only 300 million years, as was the case for a lot of the Martian meteorites. So through a process like that, we don't know where on Mars these meteorites came from. All that we know is that their composition, the bubbles of gas that are trapped inside them, are a match for what we know Mars to be. It's an interesting question. Like if you were on, let's say hypothetically, you went to the moon and you found a stray rock that turned out to be from the Earth, it's conceivable. How would you know where on Earth it came from? Right? Think of all the different compositions, all the places on Earth. So we have this same ambiguity for rocks that have come from Mars, but we are certain that based on their overall rock chemistry and also the gases trained and their age, and also their cosmic ray exposure age. Remember I was telling you we can tell how long it's taken a rock to get to the Earth? If it's from Mars or the moon, it's going to be relatively short, 5 million years maybe. But if it's from the asteroid belt, it could be 20 million years or 30 million years. Too long to have really come from Mars. So for all those reasons, they do carry a Martian pedigree. Now they don't land on the Earth with a sign saying, hey, I just arrived from Mars, right? They need to be analyzed in a lab that can do that kind of work. And that's why there is this sort of symbiotic relationship between the people who search for meteorites and find them and the academic institutions with collections of meteorites that analyze them. They sort of feed off of each other. If somebody finds a rare rock that is suspected of being from Mars, for sure, that lab, let's say the University of Arizona or Harvard University has one, they want a piece of that to study, to analyze, and to keep a piece of for their collections.
Great, thanks.
Yeah, you're welcome.
My next thing is actually an anecdote, and I'm pretty sure I know what you'll say. I brought this up here at GAAC probably a decade ago. I was viewing up at the visitor center up in Rockport at Halibut Point, tearing down my scope, and all of a sudden I heard this sound reflecting off the wall of the visitor center this way. And for some reason, I turned my head this way and I watched a meteor like spiraling in the sky. Yep. Now, I don't know if that was some weird coincidence of simultaneous sounds, but what kind of evidence is there that meteorites are ever even close to us to enough to make any kind of a sound that can be heard?
They certainly can, Alan, right? So like that Chelyabinsk impact, there's a shock wave associated with its passage through the atmosphere, and it definitely can make a sound. However, what betrays what you saw is the fact that you say you heard the sound first and then saw the meteor, or even if you saw them simultaneously, that is happening 10, 50, 100 miles away from you. And it would take a long time after you saw the flash for the sound to reach you. So I suspect it could have been, you know, one of those self-immolating seagulls that you hear so much about.
Fireflies.
Unlikely to be a meteor. I'm sorry.
Well, it was almost gone. I was looking this way at my telescope when I heard the sound.
Yeah.
By the time I looked, I just saw the tail or the head of it disappearing, and I could see the tail had been there. But
Was the moon out that night?
I don't believe it was. No, I wouldn't have been out with a telescope if it was.
All right, because that wasn't Mario shooting at it. Okay.
Kelly,
Yes, go ahead.
first of all, thank you very much. Great performance. It was very informative. And I was wondering, do they have any parts from Mars, like from Mount Olympus, where it's already pretty far off the surface and it's easy to launch? And do they actually know, yeah, this is from there? You see the crater.
That's a really good question, Arthur. So Olympus Mons is a fairly recent construct. It's only a few 100 million years old. So the age of the solidified rock would reflect that. And also would be pretty clearly basalt, right? Because that's what comes out of volcanoes generally. We know of no Martian meteorites that would match that characteristic. And you're right that Olympus Mons is very high up. The atmosphere of Mars is really thin, so friction with the atmosphere is not really an issue. And I think the little relative Olympus Mons is like 15 miles high, right? So let's put it in Earth terms. I wouldn't imagine that an asteroid colliding with, say, sea level Massachusetts would have roughly the same chance of escaping as, say, one hitting Mount Everest or the top of Mauna Kea. The heights of the mountains compared to the size of the planet are really quite small. So I wouldn't. I would think it very, very probable that we would have meteorites from Olympus Mons. There aren't very many craters on the flanks of that volcano, which testifies to the fact that they're pretty young. But you would need a crater, obviously, to eject something out into space.
Thanks for the explanation.
Yeah, no problem.
Okay, y'all, it's getting on in time here, so one or two more from the room. Anybody else have a question for Kelly?
Yes.
Is there any place on Earth that seems to be richer in meteorites than the rest of us?
I did not pay her to ask that question, okay? She asked whether there are any places on Earth that are richer in meteorites than others. Statistically, a meteorite has an equal chance of landing anywhere on the Earth. You would accept that, right? So just as you're likely to land in Massachusetts as, say, the Siberian forest, we have a better chance of finding it here. There are two places that have that meteorites are found more often. One is the Sahara Desert, or any vast desert area that's relatively stable, but especially the Sahara. Why? Because what color is the Sahara Desert? White. And if you see something on the surface that looks like this, it's going to be out of place. And so all of the nomads know that as they go back and forth across the Sahara Desert, if they find rocks that look like this, they are good chance that they are meteorites. That's one place. The other place is actually Antarctica for the same sort of reason. Think of the ice sheet that is Antarctica, right? This would apply to Greenland in addition, except that Antarctica has its continent size, and it has these movement of their glaciers that push them up the sides of mountains. And when that happens, the winds gradually evaporate away the ice, what are called katabatic winds, right? So and any meteorites that have fallen over thousands of years tend to get concentrated on the surface. And so every summer at this time of year, there's a team from the National Science Foundation in Antarctica, also a team from Japan, also a team from China and other countries, who are scouring the ice sheets of Antarctica looking for meteorites. And the first ever meteorite found from the moon, which was in 1979, was in fact a meteorite that was brought back from Antarctica. It has the double advantage of they're very easy to find because they stand out, they just zoom along on their snowmobiles, and if they spot something dark, they stop and they go get it, because it's either that or It's penguin poop. And because of the extremely dry environment in Antarctica, they tend to be very well preserved for scientific study. So it's a double plus. And I was actually asked to go down, this was back in my reporting days, to accompany the National Science Foundation team to go down. It's a 6-week stint going to Antarctica and collecting meteorites. And I said, there is no way in hell I'm going to be that cold for that long a time. Thank you very much.
Any other questions?
All right,
Oh,
to
thank
the
you,
dessert.
Kelly.
Thank you.
Will you take a comment from Zoom before we leave? Michael,
Uh-oh, Michael.
What?
will you take a comment from Zoom before you close the door?
Okay.
Okay. Many, many years ago, we were tent camping in Nova Scotia and witnessed the most spectacular meteor shower. It had to be because there's really not much light up there. One of them just lit up the entire sky on its way over. It was so beautiful. And this presentation you just did just added to the wonder of it all. I have no idea what we saw, but they were wonderful. So thank you very much. This was great.
You're right, everybody. Thank you.
I want to thank everybody who brought food. Thank you.
Have a great night. Thanks, Mike.
Happy holidays.
Happy
Bye-bye.
holidays,
Happy
everybody.
holidays.
Everybody.
Happy holidays.
Yes.
Bye. Bye.
It's right here.